Okay, it looks like it's been redirected. So thank you all for joining us for another class here in a virtual world with Bobby Farlice-Rubio. And today is "And the Mountains Crumble to the Sea," which is one of my favorite classes. And just for folks in Zoom, feel free, the way we're working it is and it looks like you guys already are on it, but on chat, or you can do the Q&A and I will go ahead and raise my hand and get Bobby's attention to answer questions that you may have. And then also we are live streaming to YouTube. And again, there are many more classes today. The next one is actually at 1 p.m., A Day in the Life of a Meteorologist. But without further ado, I want to hand it over to Bobby and get our class started.
All right. Well, good morning, everyone, and welcome to this class. Yes, the mountains crumble to the sea. Well, if you're wondering where that word comes from, that phrase, that's actually a line from Benny King's great song, Stand By Me. But it's actually a perfect reference to the fact that that's what's constantly happening on our planet. Our planet erases mountains. Mountains, none of them last forever. Even the tallest mountain in the world, Mount Everest, is losing about an inch per year of height because of the fact that it is growing up in such a violent environment. A planet with wind.
And I will go ahead and raise my hand.
Oh. Sorry, we had a time loop, fourth dimensional effect there. But yes, so back to what I was saying, speaking of time, no mountain lasts forever, and all mountains are constantly being destroyed. In fact, all of the land is being kind of destroyed and regenerated. And this class is kind of about that in a way to show you some of the things in nature that you can use to observe the effects of what we call erosion. Now, this is a perfect time to think about this because we're in mud season. If you live here in Vermont, you are watching erosion before your eyes. Their driveway, oh no, all that gravel that I drive on is washing away. It is going down the hill, and the gravel, the pebbles, the sand, all that stuff is getting carried by usually water down the driveway, out into the ditch, and eventually that ditch leads to a stream, and that stream leads to a river, and that river leads to, if you're in Vermont, the Atlantic Ocean. And so eventually all of that rock and gravel and pebble that you see is going to wind up in the sea, wind up in the ocean. So that is a fact of life, and it is something that in a place like Vermont, you can literally see everywhere in your backyard. So let me put up a word on the back of my chalkboard here. The word of the day is erosion. And for those of you who have never heard this word before, some of our younger viewers or folks not familiar with this word, just think of how similar erosion is to another word that I'm about to demonstrate here. Erasing. When I erased that word, I didn't really make it disappear. I just changed it into another form. There's the word erasing right before your eyes. I don't feel so good, Mr. Stark. No, just kidding. Sorry. I can't help myself. However, erosion creates something that we call sediment. So I don't want to block it with my head there. Erosion, sediment. We're going to talk about things like sedimentary rocks. I should have written it higher, I guess. However, before we talk about how mountains get erased and crumbled into the sea, maybe we should spend a few moments talking about what makes mountains form in the first place. Let me show you something I've got over here that is a frequent part of my classes on geology. I've got what I call lovingly the tectonic textile right here. Here is something that's meant to model how the earth works. And maybe it'll be more dramatic if I dim the lights. All right, so I think you all can see this machine right here. This is a piece of fabric that I've made to look like the earth with different layers. And the top layer would be a layer that you garden in, the layer that the forest grows in. Think of the soil. And actually soil is like half sediment anyway. Think of all the facts, the fact that part of the soil is little rocks, little grains of sand, little pebbles. So even this top layer is made out of crumbled mountains, but also organic matter, dead things like the leaves from last fall and the logs that fell over and the twigs and living things like all the worms and the bugs hibernating in it. So this layer is very active, but this layer is the one that you step on. If you were to dig deep underneath, you would see different layers of rock, different layers of minerals. You might find a layer where there's no organic matter, where everything looks like this because it's just rock, dust, and sand and sediment, and no twigs and leaves and soil, maybe. And if you go further down, maybe you'll find silver. Ooh, we're gonna be rich. Just kidding, that's just foil. Aluminum would be valuable too. Or maybe you'll find a layer of bedrock that's a bright white color, rich in quartz or silica or something like that. And then maybe if you dig somewhere else deeper, you'll find a layer of something that's red, maybe rich in iron. And that is usually what causes rocks to be red. So there could be iron minerals here. And then if you dig further down, another layer, and maybe you'll find something like coal. Coal is actually a sedimentary rock, but the sediment was once alive. So instead of it being rocks and sand, it's actually old fossilized wood and the leaves and the ferns and the dragonflies and all the bugs that crawled through that forest. So when we talk about coal, that's why we call it a fossil fuel. It's a sedimentary rock that's literally made of dead life from a long time ago. But let's keep going. Maybe we can dig further down and find, ooh, look, I found some diamonds, some sparkly stuff. Ooh, we're gonna be rich. People often find diamonds very deep down underneath the ground. And then if you go a little farther, some more bedrock, ooh, some sparkly red thing. But eventually, if you go too far down, just kidding, of course. This is just red light. But this is to imply the fact that no matter where you live, if you dig down deep enough, you're gonna get to a layer that is not exactly solid. The mantle is magma. And yes, it is connected to the lava that we see coming out of volcanoes, but this layer is so hot that the rocks are permanently molten. So that makes them slippery. It's not slippery like water, more slippery like wax, but still slippery enough. And let me stop right now because I see we have a question coming in.
Just because you mentioned silver, someone was asking, is there gold?
Well, this is just fabric, all right? But I want you to know that interestingly enough, there are mines where some of the metals are found together. That's a chemistry lesson in geology, and I'm not gonna go too deeply into mineralogy today, but gold, silver, and copper are often found together in the same mines. And if you look at the periodic table, you'll see they're in the same column. There is a reason. They're chemically similar, so they tend to react to the same minerals, and they kind of end up being found together. But sorry, this is just fabric from the fabric store from long ago. So, all right, but this magma layer here looks a lot warmer than it really is. It's just red light. But I want you to imagine that if you were to dig down at least like 5 miles anywhere on the earth, in some places like Iceland, it's a lot less than 5 miles. It might be hundreds of yards where you could dig down and find that molten layer of the earth. So because this stuff is hot and slippery and all this heavy solid stuff is resting on top of it, many of you already know that this layer is prone to movement. We call this the crust. And that crust is not stable because of the fact that it's sitting on top of a slippery, warm layer of magma. And so to get to the point here, there's a lot of things that can happen to the crust. Maybe the easiest thing to understand is that parts of it can rip. Oh, look at that. A rift is forming. Right now at the bottom of the Atlantic Ocean, the plate that has Africa and the plate that has South America and the North American plate they're all sliding apart from each other. And in the middle of the Atlantic Ocean, at the bottom of the sea, there is a chain of volcanoes made by this crack, the rifting that is actually causing the Atlantic Ocean to become wider every year, a little bit. So you may have heard of rifts like that happen underwater. And there is a rift on the continent of Africa, very similar to this, that's happening not underwater, but on land, a rift that probably played a huge part in the evolution of our species, separating us from the forested parts of Africa, leaving us in the high and dry plains that allowed us to become the walking and hand-using apes that we are. But that rift in Africa is still growing, the Great Rift Valley. And there are places like in Ethiopia's Erteale where you can stand on a cliff and look down and see that magma. You can see volcanoes and lava lakes bubbling up inside of these cracks. So there are places in the earth where you can actually kind of get a view as to peering down into the underworld of hot magma. But let's talk about what happens when these plates don't separate but come together. And I see a hand up. Yes, Leela, what's the question?
Hold on. There we go. So someone was asking, because you're talking about sort of this spreading. So how wide is the crack in the ocean? Is that?
Oh, you can actually, if I don't have them ready to go, but you can look up topographical map to the bottom of the sea, and the crack is miles wide in some places. It's basically acting like this. I'm going to do it with my hands. Imagine with my knuckles is where the crack was meeting before, but new material like lava is rolling out. So that crack is spreading kind of like a conveyor belt, where my knuckles are now very far apart, but they used to be close together. So imagine that material, as the pull separates it, lava bubbles up and it forces the plates apart. So you can imagine this conveyor belt is constantly happening. And if those of you who have access to it, if you watch the Planet Earth documentary series, a great documentary series made by the BBC and the Discovery Channel a few years ago, you can see shots from submarines that went to that trench, and they actually found smoking chimneys where life survives in temperatures of water that are above 400 degrees Fahrenheit. So that's not even the subject of my class today, but those ocean rifts are pretty cool places. They're almost like alien planets, given what creatures down there can survive compared to an ordinary fish on a coral reef, and it's definitely compared to us living here on land. So our planet has so many crazy ecosystems, and one of the weirdest of them all are the ones that hang out in those volcanic vents that are at the bottom of the ocean, especially in the Atlantic Rift and other places like off the coast of Japan. Wherever there's a lot of plate action, there's a lot of, interesting temperature effects in the water, and minerals like sulfur and other things leak out of the ground. In fact, I actually have a piece of sulfur right here. Brimstone, something that you often find associated with volcanoes. And that is something that a lot of creatures like bacteria can survive on. So there's a whole world where the energy comes from the heat of the earth, and the food comes from the stinky sulfur coming out of these gas vents, and sunlight does not play a role in the lives of the creatures that live down there. But that's another class. I'm going to get back to our topic here, unless we have any other questions, because this sliding plate tectonic action is, of course, what causes earthquakes. I'm doing that same thing they used to do on Star Trek to make it look like the Enterprise was shaking. I'm just shaking my computer, shaking the camera. However, earthquakes are something that's a part of life. But the other thing that can happen with these plates is when they collide with each other. And then you might get something else happening. Oh, a mountain range is here. A sharp, pointy, craggy mountain range made of brand new mountains. This is what mountains look like in some parts of the world, like the Himalayas or the Rocky Mountains, or even the Swiss Alps have lots of sharp, pointy mountains, because all of those mountain ranges are new. They're sparkling new. They're still growing in some cases, like the Himalayas are still rising. So you could say that those are brand new baby mountains. But Vermont's mountains don't look like this, because what formed our mountains did this more than 300 million years ago, even before the time of the dinosaurs. So let's see what the question is, Leela.
Someone just posed volcanoes.
Yes. When this is happening actively, there's going to be tons of volcanoes. As a matter of fact, Vermont used to be filled with volcanoes. The Green Mountains, Burke Mountain in the Northeast Kingdom, Jay Peak were all volcanoes. And the Franconia Notch in northern New Hampshire was a massive, super mega volcano. The whole notch that we drive through, dodging the moose, hopefully, is basically the bottom of a pit that was excavated by an explosion that sent lava and rocks flying all miles around. It would have been a terrible day. The weather forecast would have been raining lava and rocks for several days, but that didn't affect people because this happened 300-something million years ago, before humans even existed, before dinosaurs even existed. There would have been sea life, there would have been amphibians and plants that were affected, of course, by this. But this happened so long ago that the record has been muted by time. And that's actually what we're going to talk about, because the Rocky Mountains, the Himalayas, the Swiss Alps, those are fairly active mountain ranges that they're still growing. But mountains like the ones in Vermont, the Green Mountains, and all of the Appalachian Mountains on the east coast of the United States are very old, and they're not growing anymore. In fact, they're getting worn down. Instead of getting taller, they're getting shrunken by time and specifically by erosion. And there's erosion that happens like, a boulder rolling off the top of the mountain, running into the valley. That made the mountain smaller. But there's another kind of erosion that happened specifically here in Vermont and other northern places, other places in North America and Europe and Northern Asia, places that were buried by the glaciers of the Ice Age. So this is not to scale my little tectonic textile here, but imagine the mountains being much taller than they are now in Vermont back in the past when they were new mountains, instead of being maybe 2,000, 3,000, 4,000 feet tall or 6,000 feet tall like Mount Washington. Imagine 14,000 feet tall or 20,000 feet tall. That would have been possible here, but then the Ice Age happened. And imagine snow falling every winter, and so much snow falling that it doesn't melt before summer's over. And then the next winter, more snow falls, and it doesn't melt all the way before the next winter comes. So you still have last winter's snow piling up, and next winter's snow is landing on top of it. And that's how you get a glacier. And eventually, over hundreds of thousands of years, our mountains got buried by so much ice and snow that there was up to a mile thick sheet on top of our mountains. So if you've ever shoveled off a driveway with a foot of snow, 2 feet of snow, 3 feet of snow, imagine shoveling off a mile of snow. Obviously, that's impossible. Nobody could survive that much snowfall. The houses would collapse. Everything would get crushed. And that's the same with the mountains. Our Ice Age, I'm not going to go into all the different ice ages that we've been through, but the most recent one ended around 12,000 years ago. That's when the glaciers finally melted. And that's the time when the first people started living in Vermont. It's a pretty amazing thing. The pyramids in Egypt, 4,000 years old. People living in Vermont, 12,000 years old. So the people who came to Vermont first, most likely the ancestors of the Abenaki people, those folks that came to Vermont saw a landscape that had just survived the Ice Age. Everything had been eroded. Everything had been worn down to the point where the mountains looked like little lumps compared to what they had been like before the Ice Ages. So, of course, if you're going to crush all these mountains, guess what's going to happen to all the valleys and all the fields near the mountains? Stones, rocks, boulders, gravel. Anybody who's gardening in Vermont right now, anybody who's trying to dig a garden in New Hampshire too, or anywhere where the Ice Age happened, you probably will get a little upset by the fact that it's hard to plant a tree or dig a hole without encountering a big stone. You won't have to work hard to find one. They're everywhere. And all of those stones that you find underground, they kind of look round, and some of them look like they've been eroded by water, and they were by ice and water. That is all remnants of the Ice Age. And if you go to places farther south, like there's places in Pennsylvania and Wisconsin, where you can see the boundary where the glaciers went. And if you go south of that boundary, you could dig a hole 10 feet deep and never find a rock. That sounds pretty nice, but that's not the case up here. If you dig a hole in Vermont, you're going to find a rock within a few inches because of the Ice Age and the erosion and the enormous amount of sediment, both large pieces like boulders and small pieces like clay and sand and silt. All of that was a result of all of that erosion that took place for hundreds of thousands of years. So I hope you understand that when you go outside and you look at the mountains, the Green Mountains, they were much taller and they've been worn down. And you can tell that when you look at the Appalachian Mountains all over the East Coast of the United States, they look round, they look soft and smooth compared to the sawtooth, jagged teeth that you see on the Rocky Mountains out west, which are much newer mountains. They formed during the time of the dinosaurs and after, as opposed to ours that formed millions of years before the dinosaurs even existed. So let me switch back Let me lighten up the room a little bit. It's a little dark. I'll let you look at some ducks on the wall while I turn on the rest of the lights. All right, so erosion creates sediment, and we have a lot of that in Vermont. And if you want to think about what the rocks, how the mountains used to look, or how these tectonic plates behaved here, let me show you something that the USGS, the United States Geological Survey, prepared for the northern part of our state. Here is a bedrock map of northern Vermont. I could put the whole state, but I don't think you need to see the whole state to get the idea. Look at all those layers. All those different colors represent different kinds of rock. And just like the layers in my tectonic textile, they may have once upon a time been laying down flat, but something happened to them. They got twisted, they got ripped, they got smashed together. And if you look at the bottom right of the picture, you can see a cross section that's like looking into the land. And it almost looks just like my fabric. You can see how some parts of it bunched up, some parts of it crashed, these thrust faults. There's all kinds of names for this, but I don't want to bog you guys down with terminology. I just want you to realize Vermont looks like a car that barely won the demolition derby at the Caledonia County Fair. Our state looks like it's been ripped and shredded and torn and twisted. And when that was happening, when the mountains were being formed, yes, we would have had volcanoes everywhere. Vermont would have been a dangerous place to live. I don't think we would have wanted to live anywhere near all those volcanoes when this was actively happening. But that was hundreds of millions of years ago. And today everything is settled down. And you don't see most of this bedrock because, of course, it's buried by all the soil built by all the leaves of all the trees that have been growing in Vermont for the last 10,000 years or so. So this is the hidden bedrock. And I know the kids that play Minecraft are, going crazy hearing this, but yes, bedrock is a real thing. And that's bedrock for our state. And you could go to the USGS website. If you live in other states, you live in other parts of the country, you can get a map just like this for any part of our country. And if you really want to see this, you can have it printed wall size by the USGS. I think they charge something like 40 or 50 bucks, and they'll send you a poster. We have one in the main hall of the Fairbanks Museum. So you can come once everything gets back to normal, we reopen, you can see this poster, the whole state, in our balcony section. So that's a cool thing to look at. And if you look carefully, on the left side of the state, the western side of the state, where we have the tallest mountains like Camel's Hump and Mount Mansfield, you can actually see some of the rings and features that were caused by the volcanic activity. But that is mostly muted when you look at it from outside. And look at how the layers are all kind of packed together. That's because they were sort of thrust in a vertical fashion. So what was laying like this is now laying like this, and you see like the tops of my fingers, you're seeing all these different layers poking out through the mountains. But when you look at the eastern side of the state, including the Northeast Kingdom, you see a very different picture. It looks a little bit flatter, but that's actually mostly granite. Those blue and pink colors are the granite that we have a lot of in our side of the state. And granite is actually connected to volcano plumbing, so to speak. Granite is not lava that squirted out of a volcano. It was molten rock that was in the tubes leading up to the volcano that may have gotten ejected, but it ended up staying in the ground, and it froze in the pipes in the ground instead of getting squirted out. So when you see all that granite underneath us, that is also an indicator of the fact that that was the source material for the volcanic activity that was going on high above where that layer is now. The Ice Age glacier scraped down to that underneath layer. It'd be like scraping down the street until you could see the sewer and the water mains sticking out, kind of like what the Ice Age did to our ground here. So in that sense, I want to just give you a really quick introduction into the three categories of rocks that scientists use to describe rocks, because there's thousands of kinds of minerals. I'm not going to go into all the different ingredients that are in all these pieces of bedrock, but any rock that you find can be at least put into one of three categories. And that's not that difficult to do. If you think about the history of the earth and how that rock was made, you can probably 90% of the time figure it out, even if you're a beginner on this. So that word up there, sediment, well, that's going to have a part to do with this. But first, let me write another word up there. I hope you all will be able to see. Ooh, sorry about that. Ooh, those squeaks still carry through the internet, I hope. Igneous. Igneous means born of fire. And that kind of makes sense if you're thinking of a rock that came out of something like a volcano or from magma. This is the original kind of rock on Earth. There was a time when the only rocks were igneous rocks when Earth was just forming, when the magma was cooling down as the planet just formed. And if you forget what igneous means, think of ignition, ignite a flame. And then that might help you remember igneous has a lot to do with heat and fire. So igneous rocks born of fire, but igneous rocks can't last forever. Earth beats them up. The weather does things to them. The ocean tumbles them. The rivers roll them. And eventually, every igneous rock will break down and become sediment. And then there's a good chance that that rock could become a sedimentary rock. You see, sediment becomes a kind of rock made of sediments. And that is probably an easy thing to think of. If you think of rocks that look like they're made out of little pieces of other rocks, then you might be looking at a sedimentary rock. But both of these igneous and sedimentary rocks can go through another process. And that is the last word of the three categories I'm going to talk about. Metamorphic is another kind of rock. And metamorphic rocks, well, think of metamorphosis. Think of a little squirmy caterpillar turning into a beautiful butterfly. And think of a piece of coal or graphite turning into a beautiful diamond. And then you can understand what metamorphic rock means. It's rock that's been transformed by being underneath all those layers of rock, like in my tectonic textile. It's gotten squished, it's gotten heated. The presence of the magma underneath is like an oven that bakes these rocks, allowing them to have chemical changes. So you can get the crystals to rearrange themselves. You get minerals and elements moving from one side of a rock to another, concentrating in weird forms. And then you've got all kinds of beautiful things. I'm going to show you examples of all of them. But igneous, born of fire, sedimentary, made from sediment, and metamorphic, transformed rocks. And that is what we have on Earth. So if it wasn't for erosion, we wouldn't have sedimentary rocks, because erosion, the whole point of this lesson, creates the sediment that makes those rocks possible. So I'm going to give you some examples of these categories just to give you something to think about and something to maybe look for if you ever go out looking for rocks. Here is an igneous rock. This is a volcanic scoria. This is a rock that you might see if you go to Hawaii, where the volcanoes have recently belched out lava. And can you see all the pores in it? It's filled with holes because of all the gases, stinky gases like hydrogen sulfide, sulfuric acid, all kinds of things. It would have smelled like farts. But those bubbles in there were formed while this was molten, and then the gas escaped and the rock hardened. So it created permanent frozen bubbles, you could say. These are the pores that we see on a lot of volcanic rocks. And a lot of volcanic rocks are dark black like this. So if you go to places like Hawaii or Iceland, you see a lot of black rock lying around. And in Hawaii, they have beaches made of sediment from this rock getting worn down by time, turning into black sand. So if you go to Hawaii, you can step on a black sand beach made of the sediment from black igneous rocks like this scoria here. And of course, if I'm talking about igneous rocks, I've got to mention granite. Of course, New Hampshire is called the granite state, and Vermont has just as much granite as New Hampshire does. In fact, if you go to Barry Rock of Ages Quarry, you can see beautiful granite from Vermont, or the Blue Mountain Quarry in Reigate. But this is igneous rock. It didn't get squirted out of a volcano like this one. but it was still molten rock, and it froze, and all those different colors that you see in it are the different minerals that are part of that magma, including things like there's probably a little bit of uranium or thorium in here in addition to other minerals. Pretty cool. So Leela, we have a question.
Just asking, how much does bedrock weigh? So I don't know if you can
Oh,
classify like what it.
that varies much hugely depending on what the material is. So that's a question of density. Well, a lot of rock like granite is very dense. That granite, is pretty weighty for the kind of rock that it is compared to the scoria that's filled with air bubbles, right? And actually, I neglected to get myself a container to do this, but I have a igneous rock that actually can float. So this is not something you're likely to find in Vermont, but this is something that happens when volcanoes erupt. They make rock foam. We call it pumice. And if those of you who study the history of ancient Rome may know about a city called Pompeii that was lost to volcanoes. And there was a time when the Roman Navy tried to come and rescue the people in Pompeii, but their ships got stuck in the water because the bay filled up with so much pumice. It would be like trying to sail a ship through a bowl of cereal. And all that rock ground up against the ships and they couldn't move. And a lot of those sailors from the Roman Navy died too in the effort to rescue the people from Pompeii because of this filling the ocean up. So Leela, do you have a question?
I was just going to say, do you want to stop your screen sharing? Because I see that you're showing rocks. So
I'm really sorry. I neglected to put myself on full screen. So let me do that again real quick. For those of you who had a hard time seeing it, here's the pores of the scoria. That was an igneous rock filled with air because it came out of a volcano. Similarly to the pumice, they're a different color, but they're very similar, filled with air bubbles. And this pumice on the right is extremely light, low density. It has a lot of air in it, so much so that it can float in water, like I was saying about the Roman Navy. So these are volcanic rocks that you would find on the ground near a volcano. And on the brim of a volcano, you might even find a lot of concentrated sulfur that comes out of the gases that are fuming. Sometimes it deposits and creates these nearly pure nuggets of very smelly sulfur. But here is that granite. And that granite is also igneous, but it didn't come out of a volcano. It stayed underground and froze slowly, kind of freezing all the different minerals that are in it, in place. So you can actually see that it was made out of many different ingredients and it froze like that. Well, those are the igneous rocks that I have right in front of me. But let's talk about sedimentary rock. Now, I have a piece of rock that actually should look familiar because it actually is what the Fairbanks Museum is made out of on the outside. This is sandstone. And if you look at some of the pieces, you might even see the layers. This used to be sand. In fact, this used to be sand blowing in sand dunes that were where Longmeadow, Massachusetts is today. And those sand dunes, well, if you're sand in a sand dune blowing around in the wind, some of the sand gets stuck at the bottom of the dune and the weight of the sand on top can kind of squeeze and glue them together. And if they sit there long enough and they get pressurized and stuck together, the little grains of sand will become sandstone. And if you look carefully, you can see a little bright stripe right there, which means for some reason, a brighter layer of sand was blown in that year and it kind of created this mark. So this is why you see stripes in some sandstones. It depends on the color, and the color of the redness is an indication of how much iron was present. So the lack of iron in one particular year could be an indicator of something happening. Maybe something changed the life that was on the sand dunes and there was less iron for 1 year and that created a brighter layer of sand. So in a way, like sandstone and other sedimentary rocks can be used to look back in time, like the pages of a history book. You can see things that happen kind of similarly to what we do with the rings of trees. So sedimentary rock, that's just one kind. But one of the things I want to show you is a weird kind of sedimentary rock where the sediment was once alive. This is not some new kind of chunky granola, folks. This is a rock called coquina. And if you go to places like Florida, you'll see this everywhere because Florida is right by the ocean. Florida used to be a coral reef. And if you've ever been to the beach in Florida, you'll see a lot of shells lying around. And imagine how many millions of years of shells have built up over time. They pile up, they get stuck together, and they start to stick together. Water and other things like acid in the soil and in the rain can dissolve them, and they start to become one rock instead of many little tiny shells. And this is coquina that's fairly recent. You can actually still see the individual shells that are in it. But I have a piece of rock that was coquina, but the older part of it has dissolved and crumbled and stuck and clumped together so much that it doesn't even look like shells anymore. This one, you can see a transition from what looks like coquina to what is now what somebody would call limestone. Limestone, a rock that is very common, something that farmers grind up into powder and sprinkle onto fields because limestone is rich in calcium. And the calcium in the limestone goes into the soil, the grass absorbs the calcium, and then the cows eat the grass, and that calcium goes into the delicious dairy products and the milk and the ice cream and the cheese and the butter. And then you're eating calcium that once was seashells. How weird is that? So this is a sedimentary rock, but one of my old jokes about rocks like this is it is not just a sedimentary rock, it's also a cemetery rock. Oh, well, not to be creepy, but yeah, some of the rocks on Earth are literally made from what used to be living things. And limestone, that's what makes limestone. But here is a sedimentary rock that wasn't shells, but forest. This is a piece of coal. And this kind of coal is basically just a clump of partly slowly decomposed wood and soil and leaves and ferns and everything that existed during the Carboniferous period, which is when our coal beds were laid down. So sediment from life, that could be sedimentary rock, or sediment from rocks that were broken up like sand. Sedimentary rocks can come in many forms, and these three are just three examples of what could be thousands of different kinds of rocks that you can find. But to get onto the metamorphic kind of rock, here is something that's very common in Vermont. This is a kind of rock called schist. Be careful when you say that, okay? Schist actually is more common than granite in states like New Hampshire and Vermont, but nobody wants to call their state the schist state. But this is a metamorphic rock, and it actually betrays the fact that it used to be a sedimentary rock. Can you see that? It used to be layered rock. It used to be partly either limestone or a mix of different things like silt and clay, but eventually it got heated. Maybe it was sitting on the bottom of the ocean some time ago, millions of years ago, and then those plates came and crashed together, and this layer got buried underneath some other rocks. It got forced down to that magma layer. It got heated. It got melted, cooled, melted, cooled. And then weird things started happening, like these little garnet crystals. So when you see crystals, sometimes there are crystals like quartz that can be igneous, but a lot of the really crystalline rocks that you find are metamorphic. Look at that. It looks like a double pyramid. It's a pretty cool shape that these garnet crystals get. I'm hoping you can see the facets. That is part of the metamorphic rock, and it would be embedded in the rock. So if you take a metamorphic rock and smash it in half, sometimes you'll be treated to finding all these crazy crystals that come from concentrations of different minerals that are in the rock. And that is a piece of garnet schist. But here's another piece of schist with a lot more silica in it, a lot more quartz in it, and that's what gives it that sparkliness, and mica, things like that. Oh, wait, I have a cool example of that. Sometimes the rocks separate into different minerals, and when you look at mica, it's a rock that you can actually see through. In the old days, I've heard that in the colonial times, people used to make lanterns with this as the window because glass was expensive, but this was cheap if you know how to find it. And so you could make really cool lanterns with mica panes instead of glass panes. It looks like plastic, but it doesn't melt as a rock. So it's pretty cool stuff. And if you find mica, you'll probably see lots of little flakes of it in the gravel in your driveway. That's part of the rocks, like schist. Oops. In fact, oops, I'm messing up my computer. I'm foliating. I've got a thin piece that just fell off. It's really cool. So yes, we have a question, Leela.
Yeah, someone was asking how mica forms, so how it looks like.
Well, as a rock is heated and cooled, different things have different melting points. And so different minerals like silica will melt out and they might get shoved in between other layers of rock. So there might be a crack where the rest of the rock is staying solid, but some part of it has started to melt and it drips into these. So in a weird way, the metamorphic process can refine things, sort of separate ingredients and concentrate and even purify things. So you can get something like this mica mineral, which is mostly silicon, which is what sand is made out of. It's just in a very different form. So here you have that. So, think about this. Silicon, we use it to make glass. It's in sand. It's a very common element on the crust of the earth. So it doesn't always look the same when you find it. Quartz has a lot of silicon in it too, but it has a very different crystal pattern. And then when we talk about things like the limestone, we have a lot of calcium. Calcium, like my teeth. So this is the same stuff that makes your bones and your teeth in a different form. It was part of life, but not human teeth, but the shells of ocean creatures. So we can talk about that too, because if you're a geologist, a lot of what you study is also the chemicals of the periodic table, the elements. So you have to know a lot of chemistry if you want to study the rocks in geology. But I want to go back to focusing on erosion. Of course, here's some cool things. Like, look at this rock. It's a sandstone where there are holes where the shells used to be, and the shells have fallen out. So it's a sedimentary rock of a very strange form, where in some places the shells are still visible. All right, and here's one where the shells all fell out, but you can see this was igneous rock underneath, and then on top of it, a sediment started to form that was like mud, and the mud was embedded with thousands of seashells, and the seashells have fallen out, but the mud still carries their shape. So it's like a fossil of an ancient bottom of the ocean. So as much fun as that is, I want to present you a mystery. Let's see if we can get started with a cool picture. Hold on, I know you've seen that, but let's look at this picture. Here is a place in New Mexico called Carlsbad Caverns. It's a place that you can visit as a tourist in the future when things mellow out, but this is a cave of limestone. And if you know the history of the United States, ancient history, New Mexico was part of the continent that was underwater. New Mexico used to be the bottom of the ocean during the time of the dinosaurs, and then the ocean retreated, causing a lot of erosion, things like the Grand Canyon as the water was draining out of America. That's a big ditch of erosion as the continent dried out. But all the seashells that lived at the bottom of the ocean where New Mexico is piled up, and that desert is made of a lot of calcium from seashells. So when it rains, the water trickles through all that sand and it starts to drip into holes. If there's caverns, if there's any place where there's a void, that water will take the calcium from the layers up above and drip, 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 drip down onto the ground inside of a cave. So this is where you get the concept of stalactites and stalagmites. And I don't want to go like crazy with terminology, but actually this one is something that I remember as a kid learning how to remember. A stalactite hangs tight on the ceiling. So all the ones that are up on the top pointing down are called stalactites. They hang tight. And the ones on the bottom, look at the right side of the picture where you see those little cones on the right. Those are stalagmites. You might trip on them. I know it's corny, but that might help you. Stalagmites might trip you. Stalactites hang tight from the ceiling. And in this case, a stalagmite, the one on the bottom, is not that different from what you kids might do when you spill a bunch of orange juice on the floor and then the water evaporates and it leaves all that sugar behind and it makes a sticky patch. Now imagine some very mischievous kid going and dropping a bunch of orange juice on the same spot on the floor every couple of days, another drop and another splash, and that sugar crystal patch Your parents will be very mad at you, of course. But that sugar crystal patch will grow taller and taller, and eventually it will look like a patch of orange tinted rock candy from all of the sugar staying behind and all the water and the orange juice evaporating. Now, that would be a sugar stalagmite that you could make by spilling juice on your floor every day. This is not a sugar stalagmite, but a calcium stalagmite made out of the limestone that dripped from the ceiling. So if you look at the ceiling, you'll see the stalactites, which are made from that limestone that's dripping. So they look like icicles, but they're not frozen because they can exist in warm temperatures. New Mexico is a pretty hot part of the country. It's not that cold in this cave, but at least those stalactites are not made out of ice. They are made out of dripping calcium. So the closest thing to a stalactite that you might have in your house is that little dribble of maple sugar that's at the end of the jug of maple syrup. If you pour maple syrup on your pancakes, or if you pour ketchup on your burger or hot dog, there's always that little drop that stays on the tip. And if you don't wipe it off, which most of us probably won't, it will harden, it'll dry up, and it'll turn into a little tiny stalactite of ketchup or a little stalactite of maple syrup. Now imagine if you have a big jug and you have a big family and every morning you have pancakes and you pour maple syrup all over them every day, and that drop gets a little longer every day, and eventually somebody says, whoa, look at that, we've got a 3-inch stalactite of maple sugar. You can break it off of the jug and eat it. It'll be a solid, but it'll be a solid made from the liquid that was dripping the maple syrup. So if you think of that little thing on a maple syrup jug, that's a stalactite. If you think of that sticky patch on the floor that you didn't clean up, that's a stalagmite. And imagine if nobody's cleaning up anything and all of this is allowed to happen for millions of years, you get something like Carlsbad Caverns, where the dripping limestone from the ceiling has created piles of limestone on the ground. And in some places, the piles got so tall that they met the stalactite that were making them. So you've got a stalagmite going up, stalactite going down, and eventually they touch, and then they become a column of rock. And as the water trickles down the sides, you still get this big column. It's growing larger. So this is something cool because erosion is always thought of as being a destructive process. But erosion leads to this kind of rock formation. So in a way, erosion can create a new kind of rock. And a limestone cave is probably the most exquisite example of a kind of rock that is caused by sediment carried by the process of erosion into something totally new. So that's a limestone cave. But let me move on because we only have a few minutes left. So I'm going to show you a bunch of pictures, folks. And maybe I'll start with this one because this is a view that you might see if you're standing in Burlington looking west across Lake Champlain to the Adirondack Mountains. And do you see that big boulder right there on the left part of the picture? That is a sacred place to people from the Abenaki Nation. That is Ojihozo, which means the man who made himself. And if you study the folklore of the Abenaki people, you'll see that there's a story about the formation of our land that says Ojihozo sculpted our land by dragging his body across the mountains, making the mountains shorter and making the valleys wider and the rivers deeper. And in the story, Ojihozo is doing this out of curiosity to explore the land, and also because he wants to make the land better for the people to come and live here. Now, this is a folktale that might be thousands and thousands of years old, but the story of Ojihozo is actually a very beautiful description of how glaciers literally did carve our land. So I always like to think of Ojihozo as a metaphor for the erosion that made Vermont. And after all, that boulder, if I want to explain to you scientifically how that giant rock got there, Ojihozo, the rock, is a glacial erratic, is a rock that was broken off by the glaciers of the Ice Age, carried by the churning river of slow-moving ice. And when the glaciers ended their time, when they retired and melted away, whatever rocks they were holding got dropped in wherever they happened to be. So you don't have to go to Lake Champlain to see a glacial erratic. Almost everybody in Vermont has many of them somewhere near where they live. Just think of that giant boulder that's in the middle of the woods. You can't imagine how it possibly could have gotten there because it's too big to put in even a modern dump truck. And then you can realize that that was carried by the glaciers of the Ice Age. Or if you want to speak metaphorically, like in the beautiful story from the Abenaki Nation, it was carried by Ojihozo and dropped when he decided to retire. So I love that story. You should go look it up, get it from great Abenaki storytellers like Joseph Bruchac, but that story to me shows how the Abenaki folks had a great way of explaining really what happened here. Because the Ice Age, this is what Vermont would have looked like during the middle of the Ice Age. No, this is not because I have a time machine and I flew back in time. This is a picture of Greenland on top of the glaciers that cover that island. And Greenland has a glacial ice sheet on top of it that's about as thick as the glaciers that covered Vermont during the Ice Age. So this is what we would have looked like, all the mountains buried by all that ice. But 12,000 years ago or so, our glaciers melted. And then you would have seen a landscape similar to this. This is in Alaska, where they have glaciers that are melting now because of climate change. But 12,000 years ago, Vermont would have looked a lot like this, where there would have been ice glaciers in the rivers in some places. And if you look on the right side of the picture, on the foreground, you see trees and plants growing on islands of land that have been exposed longer and have given the plants a chance to start growing. But look at the sediment at the bottom of this glacier. That's what I want you to really think about for a second. All of that dark stuff mixed in with the ice, that's sediment. That's the rock that it scraped off of the mountains as it slid through the valley. And as you see the glacier melting in this picture, you can see the sediment is being dropped in creating islands, kind of like the story of Ojihozo, creating land and making rivers wider. And that glacial island there that made of sediment will probably contain rocks, eventually sedimentary rocks made from that sediment. So this is something that you can imagine if you ever go back to Burke Mountain and look at the Willoughby Gap, that you can see when you're on those trails. That gap was carved by glaciers pushing their way through the mountains, breaking rock, cracking the bedrock, and Lake Willoughby that sits at the bottom of that gap was dug out by a glacier too. So erosion can make huge changes to the landscape, dig out lakes, flatten mountains, carve out river valleys. That's erosion, but that's a very dramatic erosion that happens when you have glaciers. And that's a kind of erosion that always takes a long time, hundreds of thousands of years, millions of years for a glacier to carve out a place like Lake Willoughby. But here's a picture from Lake Willoughby of Wheeler Mountain. That's a place that's a great hiking trail if you want to do something when it gets a little warmer and the trails are a little drier. But if you look at that shape, you can actually tell which direction the glacier was coming from. There's a word for this, sheep's back mountains. A lot of New England's mountains have this distinctive shark fin shape. The glacier was approaching from the right-hand side of the picture. So as it was going uphill, it tended to slow down and deposit more material than it removed. But when it went to the top of the mountain and it hit the top, it would go downhill. And the downhill acceleration, like if you're riding your bike, you go a lot faster going downhill. And that downhill would allow the glacier to carve out the mountain. So if you pay attention to that feature that you see in this picture, you're going to see it everywhere. Camel's Hump, all of the mountains in Vermont have that distinctive shape. The north side, where the glacier was coming from, has a gentler slope, and the south side generally is where you have the steeper slope. This varies from place to place depending on how the glaciers moved, but this is something that you can see anywhere in northern New England or any place where the Ice Age happened. So, oh, hold on, I got to play this for you. Leela, let me know if you have any questions. I know we're running low on time, so I have a lot of quick things I want to show you, but this is the landscape that the first Vermonters would likely have seen 12,000 years ago. A place with gravel, sediment, sand, clay, and very little plant growth because the plants had barely had enough time to colonize the land yet. That was at the end of the Ice Age. But there would have been lots of river valleys filled with gravel. This is what our land looks like now, except we have all this soil burying all of this. But if you're wondering why there's so many rocks in your backyard when you're digging a garden, that's because your garden probably used to look like this until the leaves filled in the gaps and created the soil layer that the forest allowed to happen. So here's the glacial front. As you can see, a glacier moving down a river. I imagine that there was a time when St. Johnsbury would have looked like the foreground of the picture and Lyndonville would have looked like the background of the picture heading off into the distance. But of course, these are not pictures from Vermont. They're from places like Montana and Alaska. But one last thing I want to mention about glacial erosion. This is an esker. This is a feature that glaciers make. While the glaciers are rolling across the land, there are actually rivers of melted water flowing underneath them. And those rivers follow banks that are made by ice. So as these rivers deposit sand, as rivers are prone to do, the sand is held by ice banks. But then one day, after the glacier melts, the banks of the river melt away, and all that's left is the sand following the exact path of the ancient river that made it. So it's sort of like an inside out inverted riverbed. It looks like a hill, but it was the bottom of a river. Now it's the top of a hill that is a serpentine shape following the meandering path of whatever river under the glacier that carved it. This is a cool feature because if you live in the Northeast Kingdom, if you live anywhere between the towns of Barnet and Burke, up and down the Passumpsic River, we still have a huge esker that is a leftover of the Ice Age. And for the town of Barnet is where they get all their sand. And there are lots of private businesses too that excavate this sand in order to use it for building roads and for building houses and concrete. And all the snow plows that are spreading sand on during the winter, they're getting the sand from sources like this. These sand quarries or the sand pits that we have in the Passumpsic River Valley are all leftovers from the Ice Age. And these are real pictures. You can see this is students from what was Linden State College, now Northern Vermont University, studying the layers. Just like other sediment, each layer was caused by a different time period. So these are like pages of a history book made of sand and sediment. So here's an erosion esker, an esker when it's firstly formed, when it's first revealed. So just think about places in Vermont that used to look like this that are now covered by trees and grass and plants that have hidden that ancient history. This is what a post-glacial landscape looks like when the trees and the grass and the plants start to colonize the ground. It starts with moss and lichens first. The moss and the lichens die and they create soil, and then bigger plants can actually grow in that soil like trees and grasses and flowering bushes. So just imagine all of that, what happened with erosion. That's slow motion erosion. But here is a picture of something terrible that happened in 1 minute. This is a town in Washington State that a few years ago had a landslide. If you look on the picture on the left, that is a small neighborhood, a little road with about 30 houses on it. And one day, on a Saturday morning, there was a rainstorm. And it's sad that it was on a Saturday only because there were more people at home than usual. During a Monday, most of the people would have been at work or at school. But on this Saturday morning, when most people were in their houses, a rainstorm in Oso, Washington caused an entire hillside to come crashing down. And it killed dozens of people. Some people survived miraculously, but you can see in the picture on the left that the erosion that caused that landslide had already been happening before. There is evidence on that hill that this kind of landslide was prone to happen there. So it's a shame when these folks bought these houses, they did not think it was a dangerous place to live. They assumed that if somebody built a house there, it was a safe place to be. But this shows you how paying attention to erosion is incredibly important. If you don't pay attention to this, it can cause devastation. If you ignore the signs of erosion, you could lose lives and property and entire neighborhoods. But here's a less dangerous and more funny version of erosion, where someone in Jackson Hole, Wyoming built a house on top of a pile of sediment, not realizing that sediment is prone to washing away. So their house is also washing away. And that's erosion too, causing the destruction of a home, but in a slow fashion. Nobody was harmed by this. But what about this erosion? Here's erosion that was caused by the wind. This isn't water-based erosion. This is a sand dune in Namibia. And erosion caused by the wind can happen in dramatic fashion too. If you study the history of the United States, maybe you've heard of the Dust Bowl. Here's a picture of a town in Texas about to be swallowed by sand and dust from Oklahoma, where the wind comes sweeping down the plain, like the musical says. Oklahoma's a windy place. And during the 1920s and 30s, there was a series of droughts that dried out all the farmland. And the farmland, crops could not hold the soil together. So the wind picked up the land and blew it all over the place, causing enormous numbers of people to be displaced. Entire towns were buried by the wind erosion that we call the Dust Bowl. It destroyed farmland, and humans learned a huge lesson then, because the thing that would have prevented this from happening would have been to allow some of those wild prairie plants to still grow in that region. when farmers moved into Oklahoma and Kansas and northern Texas, they started plowing up all these weeds, thinking that they were just wasting the fertility of the land, and they replaced them with things like corn and beans and wheat, things that do not have deep roots. So plants that are adapted to a desert-like or grassland environment have deep roots because they know droughts can happen and they have to go down 15 feet to find water. Crops that you grow in a field will not have roots like this. So when they replace the prairie weeds with crops, they accidentally created the conditions that made the Dust Bowl possible. So erosion can cause all kinds of problems, and it's not just water erosion, there's wind erosion and the ice erosion caused by glaciers. And then there's stuff like this, a rock slide. This is on a vineyard in Italy where the family that lived in that house was spared because the rock crushed all the cars in the garage, but missed the part where everybody was sleeping. That's a scary, close call. But I don't think any plant roots or anything you could do could stop a boulder like that from rolling down the hill. That's a rock slide, another dramatic form of erosion. And then perhaps one of the scariest forms is a sinkhole. That's a town. This is actually Guatemala City. And you can see that an entire city intersection disappeared because Guatemala City, like many cities in the world, including Paris, is built on top of limestone. And if you live on top of limestone, then you might have caves underneath your town. And all that trickling that makes the stalactites and the stalagmites eventually weakens the ceiling of that cave, and the cave can cave in. But if you live on top of the cave, you don't know that that cave is there until all of a sudden you have this giant hole plunging 100 feet down into the cave. And that's what we call a sinkhole. Places like Florida, where all that coral reef, limestone I was talking about, Florida is one of the places in the United States with the most sinkholes. And if you think about what Florida is made out of, it makes sense. It's a very dangerous and deadly form of erosion because it can happen so suddenly. Many people have died from being swallowed up by sinkholes. So I'm going to end it now because I know we're just about out of time. And I thought I would end with a nice, peaceful picture of a rice paddy in Bali, in Indonesia, a place where it rains an awful lot and where they like to grow rice an awful lot. And rice is a plant that requires almost complete saturation underwater for a long period of time. So the fact that the farmers in Bali figured out how to grow rice on a hillside is an incredible feat of ingenuity. We call this terrace farming, where people carve the land into shapes that look like staircases so that they can prevent erosion from destroying their fields. Just imagine if they hadn't shaped the land this way, if they left it shaped like a normal hill. If you tried to plant rice, it would just wash the hill away, and eventually you'd have no farmland and no fertility. But by building these terraces, the farmers that live in Bali have been able to use these paddies for hundreds of years. So you can't beat erosion, but if you understand it, you can outsmart it, you can slow it down, you can take advantage of gravity and not let it destroy your fields, but help it fertilize your fields instead. So maybe that's a more happy way to end that than when seeing a sinkhole or a landslide. But yes, erosion. If you don't know about it, go outside after it rains and you will learn all you need to know just by standing on a ditch or on the side of a driveway. But I hope you enjoyed that lesson. And I hope to see you folks out there somewhere picking up rocks and finding out what's in your backyard. But now at least you know why it's so hard to plant a tree in Vermont.
Well, thank you so much, Bobby, for all your wonderful information. And I think today is a perfect day. It's raining right now, so it's a great time to go check out that erosion, like you just said.
Yeah, it's going to happen. It's inevitable.
All right. Well, thanks again, and I appreciate all your answering all those different questions that we had today. And of course, we will be back at 1 o'clock with a day in the life of a meteorologist. So take care, and we'll see you.
Stay well, everybody. See you, Leela. Take care.
All right. Bye.